Okay, welcome back, everybody. Looks like we have a small Thanksgiving crowd today. Anybody watching the World Cup? You people? You watching the news? What's the score? Okay, France 4-1. Okay, so that's what I saw before I left. Great. I just, data visualization about the World Cup. One example that I like is the 538, kind of like the outcome predictor, which is like a live probability visualization of each game. And so here you saw earlier, like at the halftime, France was leading 2-1. And essentially, like at the beginning of the game, France had like a 65% win probability, and Australia something like 5 or 10%, right? And you see how every goal that changed, and I think it's pretty intriguing to see, like, here's like a boring tie, and the boring ties always look like this, right? Whereas the interesting games like Argentina versus Saudi Arabia, they have this kind of like extremely jagged pattern. Okay, but today's topic is filtering and aggregation. And so what we will be talking about is like, and we talked a little bit about some of the things already. We talked about this when we talked about interaction, like how do you dynamically filter and brush. We did talk a little bit about aggregation when we talked about clustering, but today I want to take a little bit of a kind of like a more systematic approach, and just let me check whether the mic correctly set. Yes. Okay, and so the two things that we want to think about today is, well, fundamentally, how can we reduce the data, either by like filtering, or how can we reduce the data to by revealing higher level structure, right? So kind of like you can remove some items that you don't care about, or you can try to replace the items you had with something that tells you more about your data than or that is informative about your data without forcing you to visualize all of the items. And so, this is kind of like the figure from our textbook. If we filter out the items, we like reduce the number of rows in a table, and so we get from 5 to 3 in this example. If we filter out attributes or dimensions, we reduce the dimensionality of a data set. Whereas aggregation is kind of like a different beast. If we aggregate items, right, we reduce the number of items by creating a replacement item that kind of like represents multiple items at the same time. And if we aggregate the attributes, we do the same thing for the columns. And so, the classical examples here would be like multidimensional scaling, or projection methods for the dimension reduction, right? And for the items, we will do something like clustering. So these are the things that we'll be talking about today, and we'll start off with filtering. And so for filtering, we're thinking about how can we eliminate elements. And basically, the question is, what does filter strive? And the answer is like any possible function that partitions a data set into 2 sets, right? That could be something as simple as something being bigger or smaller than X value, or a fold change, or like filtering out noisy or insignificant values. Or it could be some complicated function that you might have to program, right? Especially if you have more complicated data. So that's pretty easy. And we talked a lot about dynamic queries and filters already. So the principle of dynamic queries is create these filters on the fly, and also by coupling between the encoding and the interaction, so that users can immediately see the results of an action. So remember the video with Ben Schneiderman and the home finder, where we also did a redesign, right? He was very excited that he could drag a slider and the lights on the screen would light up or be removed. Just like an interesting distinction is that queries and filters are super related. Basically, both of them are used to subset data. But the difference is that queries, you start with 0 and you add items. So you would, if you run a search in Google, it would be a query, or if you run a search in a visualization interface, it is a query. A filter is the opposite. You start with everything and you narrow it down, right? And the filter kind of like makes sense, especially when you like have this overview first, zoom and filter, details on demand paradigm. So which approach you take depends on your task and on the dataset size and whether you have a good overview, right? If you don't have a good overview and your dataset is huge, you probably want to start with query. If you have a reasonably sized dataset that you can have like a nice overview visualization for, you might want to start with an overview and then let people filter down. And so this item filtering, this is kind of like the traditional example when we first had these interactive item filters in the 90s. This is like the film finder, which is like a tool that was built around the same time as the home finder by the same group. And here on the left, you see all movies from 1920 to 1995. And then on the right, you see the movies that have Sean Connery in them that have a runtime length of 16 to 269 minutes, right? So that's kind of like obviously now with like less items on the screen, you can label them, you can actually read them very closely and so on. So all of this is kind of like intuitive and makes sense to us. One thing that I also mentioned already is this idea of scented widgets. And scented widgets is like the principle of information sent is to give somebody like a perception of the data as they're interacting with some widgets. The goal here is to lower the cost of information foraging through better cues. So for example, if you have like a filter here on a numerical vector, you can show a histogram here on top, and you could have like by having that histogram here on top, you kind of like know roughly how many items your filter will remove, right? So if I'm in this region here and I move my filter one tick over, I know that my filter isn't going to have much of an effect. But if I, of course, I'm in this region here, I know that my filter here will have a lot of effect. And then you could also just like in a simple list, you could visualize the size of a data set, right? By, in this case, color. Like this is like a data set selector. You could give an indication of how big is a particular data set. Or you could have like categorical attributes on top of widgets. And so that's kind of like a cool way of combining traditional user interface elements with visualization tools. And you can take this a step further by creating these interactive legends. And I think this is a really cool idea. So whenever you have to do a legend and you want to provide some interaction, you should think about doing something like this. So here is like a simple example. This is like a network diagram here on the right. And here you have your legend. And the legend has this interactive, these interactive handles on top of it. So you can filter out nodes that are below a certain size and nodes that are above a certain size by dragging these handles, right? And so you can have in the same space that you provide the legend, you can also provide really nice interaction modalities on top of it. So this is like, works in like whenever you have a legend. For example, if you just had a legend for, let's say, categorical values on top of a map, why not just have like the legend be interactive that you can click the countries or the states or the categorical values that are being displayed. And so dynamic queries, as I mentioned, are very common and useful and actually in visualization interfaces. This is the tree search interface that I showed before. I just wanted to show this here. It's like here you put in some query and then the system searches a very large database of items and you get like the result of this is like this nice subset. So much cleaner than trying to do an overview first. And then something that we haven't talked about are sketch-based queries, right? Sometimes I can kind of express a query numerically. I know which categories I care about. Sometimes I might have like a more vague idea about what I'm looking for. I might just have an idea of a kind of pattern that I'm looking, right? Or I'm looking for stops that dropped and then rebounded very quickly, right? Or I'm looking for elements that are in like a circular cluster. And the idea of sketch-based queries is that we can just let people sketch it. And this isn't specifically a visualization, but if you're like a computer science grad student, you might care, like you probably write some work in LaTeX. And if you're anything like me, you don't remember every command out there, especially for symbols. And so you can just draw it, right? Like I'm drawing here like a pie, and it will give me the various kind of like options. It's either the product or the pie, or I can do something like this. And I get my theta, or I get my circle with a dash in it, or I get my these other symbols, right? And so that's kind of like a useful thing that I actually use all the time when I'm writing LaTeX myself. And then, of course, we can do this for data visualization. And so this is like a really nice paper, but that is really like about time series, like querying in time series. And so I'll just play this video because they explain it pretty well in that paper. So this is just a dynamic time series visualization here. And now I can draw queries. And you can also like, here you get some approximation of the query, some mathematical approximations that you can then use. But here it would be like a hard written kind of thing. And you, by using something like this, you can kind of spot the outliers, right? So the hard rhythm is pretty regular, but here is like the one outlier. Okay. Great. So that's all I wanted to say about filtering. And now the main topic of today is about aggregation. And so aggregation is like replacing elements, like a group of elements, by a typically smaller number of derived elements, either the items or the attributes. And why do we aggregate? Of course, because we have too much data to visualize everything at once. And we can kind of like we've already talked about many of those things here when we talked about tabular data, right? We had these kind of like distribution plots, and these distribution plots are essentially aggregations of the data. Today I want to talk a little bit more about these more sophisticated aggregation approaches. So first, one thing that we haven't talked about is spatial aggregation. And this is like a really tricky piece, right? The spatial aggregation boils down to the modifiable areal unit problem. So in characterography, changing the boundaries of the regions used to analyze data can yield dramatically different results. So for example, if I have the like points that are distributed, something like this, the yellow ones here in the background, and I have a regular grid of it, and then I have like a heat map, that gives me kind of like this pattern where this cell here is blue, but then everything else here kind of tapers off. Whereas if I change the units, how I aggregate them, that has dramatically different results, right? Here it looks like there's like a very dense cluster out here, and here it looks like this is all even. And of course, this is like, it matters here, like how I draw my boundaries. And if we had some kind of like regular physical phenomenon, that would be easy, right? We would just do some regular sampling. But people, especially on the surface of the Earth, people then tend to be not regularly distributed. And so this is like a very, very big problem in anything that is related to maps. And we kind of like live with the consequences of how hard this is in our kind of like political lives, right? Because gerrymandering is the result of this. So like, gerrymandering is this practice of slicing up congressional districts such that it is beneficial for your party. I don't know how many people here are familiar with these details of the American electoral system, but the way it works is that a state has a certain number of representatives based on the population. And the principle behind this is that like a representative can is actually meant to represent a certain district, right? They have an assigned area that they represent. And that district is can be and must be redefined. So for example, after every census, districts are redrawn because the number of Congress people assigned to a state might have changed. And as you can see in the previous example, depending on how I draw these districts, I can get drastically different results, right? And of course, people have realized this, and the result is districts like this here in Pennsylvania, right? And so what's the problem with gerrymandering? So let's suppose we have 50 people here that are kind of in this square spatially divided. We see that we have 60% are blue, 40% are red. And if we had to, if we drew our district here exactly representing the columns, we would get perfect representation. So we get 3 blue districts and 2 red districts. Obviously, drawing something like this is in spatially is not possible, right? I could also draw something that is compact but unfair. Like here, for example, I've drawn the district such that blue wins all of the districts and red wins 0 districts, even though red also has actually 40% representation in that particular unit, right? Or you could even take a more extreme example. You could kind of pack the districts such that you kind of win a slight majority in many of them, in most of them, and lose by a landslide in others, right? And that would be the example here, where even though blue in this case has a majority, red wins, get 3 red districts, right? And that's what gerrymandering is all about. And so here is an example from gerrymandering in Pennsylvania, right? So this is the at the time when this was taken, this here was the gerrymandered map. The outcome here, this was the Clinton-Trump election, would have been that in Pennsylvania, Clinton would have won 6 districts, Trump would have won in 12 districts. If we had a possible nonpartisan map, it would be 7 to 11. And if we had an extreme gerrymander, you could have kind of drawn a map that where Trump would have won in 15 to 3. And then in Pennsylvania, they actually changed the map. A court decided to change the map for 2018. This was the map for the 2016 election, which obviously you can look as not compact at all. It's kind of has these weird chips in it. And then the court mandated that the Pennsylvania changes their map to a nonpartisan version of it. And you can see that this here, the districts look much more natural. And it looks there's some starker differences, right? There's well, yeah, we can analyze this in detail, but in the end, we can see that in the first case, Republican won 55% of the House votes and won 13 of 80 seats, which is way more than 54%, right? And in the other one, they won 45 of the House seats and still won 9 of the 18 seats, right? So there's the challenge here is what are our criteria? How do we draw these maps, right? There is no perfect solution. There is no nonpartisan solution. As long as you want to have somebody represent actual ground on the in the country, then this is never going to be completely fair. But you can definitely think about fairness in these kinds of things. And obviously, Utah is a good example also for gerrymandering. Utah used to have, until 2002, it used to have only 3 representatives in Congress. And the way it was sliced up is it was kind of 2 large urban districts and Salt Lake City. And then post 2002, after the census, this was updated to essentially slice up Salt Lake City into 4 congressional districts, right? So depending on where you are in the city, you can move to between 4 different districts in half an hour, right? And of course, the consequence is that people in the urban area who tend to vote more liberal, they're now sliced up, and they have the result of this is that essentially there's no chance that there will be a liberal congressman in Utah as long as this map here is valid, right? And so this is kind of what's happening. Here would be a hypothetical nonpartisan map, right? That would be more representative of the actual electoral of the actual votes in the state, so that there would be something 3 Republicans and 1 Democrat in Congress. But in practice, because the way it is sliced up, it is of course all Republicans. One way to do these geographic divisions is by using a Voronoi diagram. And the Voronoi diagram like answers the question that, like, given a set of locations, for which area is a location N the closest? So think about it. I'm flying on an airplane, an engine explodes. Where is the closest airport, right? You want to have a Voronoi diagram of the world for that, because then you can just look up, I am here, the next closest airport must be in my Voronoi cell. I can fly to that particular airport. D3 has a Voronoi layout. And here's this example with the world maps Voronoi diagram. So these are actually the airports of the world. And you can here like rotate and zoom in. And you of course see that like on the eastern seaboard, there's lots of airports. It's very dense, but then above the oceans, we have these very large cells, right? So you probably are hoping that if you're somewhere here, that you don't have an engine explode on you, because it's going to be like a long flight till the next airport, right? And so like this is like a pretty cool approach that you can use for many different things, including for interaction, right? And I've showed this before, so I'm going to go over this a bit quickly. But it has these kind of like, you know, if you have these Voronoi cells, you can simply hover anywhere in proximity to get something selected, right? So here in this example, I have to select fairly accurately. Well, here's the Voronoi one. So I can kind of be pretty sloppy about my selection, right? I have small points, and they're still nicely selected. Whereas if I have this here, I have to kind of like do very precise interaction, right? And that's kind of tricky to do. So I can't even see some of the tooltips because I'm not interacting precisely enough. So how do you create a Voronoi diagram? Well, the way it works is you calculate a Delaunay triangulation. And so Delaunay triangulation is you have a set of points. And like first the triangulation is you have a set of points, and then you just draw triangles connecting these points, right? And the Delaunay triangulation has this special property where if you draw a circle around the 3 points of a triangle, no other vertices are in that circle described by this triangle. And the Voronoi edges are then perpendicular to these edges. And so here's like an example of what I mean with a Delaunay triangle and not a Delaunay triangle. So here, like you have a triangle, and if I draw a circle through these 3 points, I would have this other triangle's point here within that circle. And that wouldn't be a Delaunay triangle, right? And so what I can do now, if I want to construct a Delaunay triangulation, I can simply flip this edge here. Instead of like connecting these 2 points, I'm connecting these 2 points, right? And then for both of these circles, the Delaunay property holds. So you can see that the circle inscribed by this here doesn't include this point, and the circle described by this here doesn't include this point, right? And if that is true, you simply like here you have your circles and your Delaunay triangles, and then you simply draw a perpendicular line between kind of like the point that you have and the line here, like a perpendicular to the edge. You draw it out, and then you see where it intersects, right? This is like what's happening here. This point here, perpendicular to this edge, keeps connecting to the next point. And so this is how you create a Voronoi diagram. Any questions about this so far? Yeah. Because then you wouldn't, like, it's about this property that you guarantee that at any point you have a clear decision boundary at what is the closest centroid, right? And only if you have the Delaunay, triangulation, does that hold. Like if you have any other triangulation, you can construct cases where the Voronoi diagram or the diagram that you're creating later doesn't actually hold that property. Okay. Great. So then I want to talk about clustering, which is going to be like a major topic for today. I'm sure, like, who's taking an algorithms class here? Like, okay, most people. So great. So this is going to be familiar then. So clustering is a classification of items into similar bins. It's based on some similarity measure, right? So if I have like an item and like a numerical vector, I can calculate, for example, the similarity of 2 points by calculating a distance like the Euclidean distance, right? Or the Pearson correlation of the 2 vectors or anything like that. And when you cluster, you use these kinds of similarity measures to group items into similar groups. And there's like 4 types or 4 classes of clustering algorithms. These are the partitional algorithms, hierarchical algorithms, bi-clustering, and fuzzy clustering algorithms. And so partitional algorithms divide data into like a set of bins, right? K-means is the classical example. I have a set number of clusters, and I want to divide my number of my data points into the 3 clusters. And then for aggregation purposes, I can represent my cluster with like as one single data point instead of as all of the points that make it up, right? And the number of bins in a partitional algorithm can either be manually set, like in the Kmeans case, or it can be automatically determined. So for example, affinity propagation is a clustering algorithm, or DBScan. These are partitional clustering algorithms that where you don't specify the number of bins, you do still specify something else that probably correlates with the number of bins, but you don't set like a hard number of bins. Hierarchical algorithms produce a similarity tree that I can then later use to kind of like create discrete bins by cutting that similarity tree. I'll talk more about this in a minute. Bi-clustering algorithms cluster both dimensions and records simultaneously so that you get like an overall optimal clustering. And that is, of course, only something that if you have like lots of numerical dimensions and lots of numerical items over them, you might want to do that. So for example, if you have like something like a gene expression experiment from a population, you might want to do something like this. And then fuzzy clustering is this kind of like the observation that partitional algorithms, like nothing, like the world, like we like to think in categories, but the world really doesn't fit into nice categories most of the time, right? Fuzzy clustering kind of acknowledges that. It's not easy to just say you're A or B, but there's like a spectrum between A and B. And fuzzy clustering more or less gives you a probability of belonging to a particular cluster. And this is like great conceptually, but also hard for visualization purposes, especially for aggregation, right? Because like you have to kind of make some cutoff somewhere. If you want to use it for aggregation, you have to kind of consider some points part of a cluster. Otherwise, you can't really aggregate it. So fuzzy clustering, conceptually awesome, difficult to deal with for visualizations, but also like an interesting research topic. So clusters can be used to order, right? When we talked about adjacency matrices and heat maps, we talked about how important it is to have this seriation. They can be used to brush. So when we have any kind of geometric techniques, right? So I can brush all of the elements in a cluster. And of course, they can be used to aggregate. And the aggregation really works because clusters tend to be more homogeneous than the whole data set, right? So you're more likely to like be able to do some efficient representation of an individual cluster than of a whole data set, because the items in the cluster are in the same cluster because they're of the same kind, right? And we can also use like the statistical measures that we can create on a cluster or like the distributions and so on. They tend to be more meaningful than for a whole data set. So recall this figure here. This is like where we used clustering to show structure in a very large experiment. And compared to if I have like a visualization technique that doesn't use clustering, it's really hard to see. Here's like a detail on how you can do cluster comparison, right? So clustering is never perfect, and there's always like a lot, like any of these algorithms that we're talking about, right? They really depend heavily on parameterizations. Lots of it is kind of like a loop where you have to get like feedback on what's going on and like visually inspect them. And this here is a tool, for example, that allows you to have 2 different clusterings here of the same data, and then like say, hey, I want to compare this cluster here. Where do the elements in this cluster lie in this other clustering algorithm? And here's like an example where we have like, you know, this is like a complicated data set, and this was split into clusters. Yeah, here this is split by some categories. And what you can then, because this is split into clusters, you can do these very compact representations. So basically, this thing here in the middle shows you the whole data set. And then above and below it are the clusters that have like a lower than average or higher than average value. And you can see that here is like all reds, and here is like dark, and then red, and so on. And so you see these patterns, the blue and the orange one, for example, become kind of like spread out over these different clusters. And so it's just like a different approach of like visualizing complex data. And so like a traditional clustering algorithms that we frequently use, and it's still super useful, is Kmeans. The goal of Kmeans is to minimize the aggregate intercluster distance, or also called the inertia. And so you basically like you try to minimize the sum of the elements in the cluster and overall the distances within the cluster. And so what you do is you have like a cluster centroid and the points in that cluster, and you measure the square distance between them. You calculate the square distance between them, and that's for each cluster, and then for all of the clusters, and that's what you globally want to minimize. And so if you can solve this equation, like if you can optimize this equation here, you get the perfect cluster solution. The problem here is that, like, of course, this isn't easy to do, and so we have some heuristic algorithms. And so the standard implementation for Kmeans is Lloyd's algorithm. And so you have like as input a set of records from x1 to xn and the k. So the k is given by the user. That k is the number of clusters. This is where the name comes from, right? Kmeans. So you pick the k starting points as centroids. And so that's kind of like the interesting piece here. Like you simply take whatever, if you have k of 3, you take 3 points out of a data set and you treat those as your cluster centroids first. And then you run a loop while you're not converged. For each point in xi, find the closest centroid cy, right? So you basically simply calculate the distance of every single point to all of the centroids and then assign the point to the centroids that's closest to it. And then for each of these clusters that are generated from that step, you compute a new centroid by doing a weighted, like an average of all of the elements in that cluster. And then you repeat until convergence. And convergence can be something like no point has changed the cluster, or distance between the old and the new centroid is between a certain threshold, or you have reached the number of iterations that you have manually specified. And so here's kind of like the intuitive version of this algorithm, right? So I start out with this data set here. The squares are my data points, and the circles are my cluster centroids, right? And first I calculate which points belongs to which centroid. And so it's pretty obvious, right, that these points here, like this point here, belongs to the red one, these points here belong to the green one, and these points here belong to the blue one. And so we can see that this isn't probably the perfect cluster, right? So more intuitive would be something like this is one cluster, this is one cluster, and this is one cluster, right? So we're not done yet. But now the next step is we update our centroids. And so when we update our centroids, the centroid here moves from this from up here to down here, because there's only a single point in that cluster at that time, right? That, like, of course, the center, like the position of that point is the position of the centroid. And similarly, this point here shifts down a little bit, and this point here shifts up, shifts down a little bit, right? And then I reassign my clusters, and now I'm kind of like getting like here, these 2 points are here, like are added here. So I have the circle on top of the third point. I have my green point down here. The blue centroid has moved up a little bit, right? And so if I kept doing this, the centroid here would move down here now. This centroid here would move down here now, and this centroid here would maybe, like, you know, it might move not all that far, but it probably in the next step, because the green one is going to move, these blue points would be assigned to the green cluster, right? So that's how Kmeans works. Any questions about this? So there's this cool tool that you can play with. And let's say I'll start here. Like, I'll pick some points, and if I do something like this, and then I click go, now I've assigned these points to the clusters, to the red, blue, and green cluster. Now I can update my centroid, and you see how these points have moved. And now in the next iteration, we can already see if we reassign the points, we will actually have like a perfect clustering solution. Then we update our centroids, and now we've kind of reached equilibrium, right? So that's pretty easy. Let's see if I play, like if I do a little bit more, let's say, difficult assignment, or I do like a very suboptimal assignment of cluster centroids, right? So if I do that, well, still, this is maybe such a simple example that this will show show up pretty quickly. Let's see. Let's have another pattern. Well, this here is gonna be tricky for Kmeans to do. Even if I give it good initialization like this, right? What's gonna happen here? So like everybody would probably agree, like every human would agree, that this is one cluster, this is one cluster, this is one cluster, and then the whole ring of the face is one cluster, right? These are the patterns that are in the data set. Of course, Kmeans is not really good for this kind of data. So what will happen is I get this kind of like spatial division here, right? So and if I keep updating this, you can see that I get this like sliced up, and it's not really the kinds of points that you would expect. And so if you have a pattern like this in your data, you shouldn't use Kmeans, right? And then another thing that is interesting, maybe we'll go back here for a second, is choosing points, right? So like here, I picked them initially, but if I do a random assignment of points, and let's do this Gaussian mixture again, and then I add centroid 1, 2, 3. Well, yeah, it's gonna just, oops. Random assignment, Gaussian mixture, add centroid 1, 2, 3. Random is like a method, and that will work just fine. I guess in this case, well, no, I found like a bad assignment, right? So one thing that you see here is, well, what can we tell? What can we know from this case that I've just shown here? Like, maybe let me ask you a question, a yes/no question. Can Kmeans always find our globally optimal solution? No, obviously not, right? So it depends on the initialization. Kmeans has like there's the heuristics about how you initialize your points are going to make a big difference. And so choosing your points initially is important. And so if we, like, for example, you could change use a farthest point method, right? So I could add a centroid, and the first point I pick is random, but then I pick the farthest point from this, right? Like calculating the distance here, and now this is going to be great. And now I kind of pick the farthest point from the mean distance, from the mean point between those 2 points, right? And so now my initialization, of course, is great, right? I just have to run a single cycle, and I'm gonna be done with this particular simple example. So random assignment, not so great. Farthest point is good, and this is like, if you use something like scikit-learn or any other machine learning libraries, they will already have this initialization with farthest points in there. The other big problem with Kmeans is choosing K, right? So choosing K isn't all that easy. In this simple 2D example, right, we know, but if I don't choose my K correctly, like here I have like a 3-cluster situation, and I've chosen K as 2, and here I have chosen K as 4, right? And even in the 4 case, this doesn't like result in a situation that I would, or even the 3 case here, I have a situation that doesn't really work for me so well. So choosing K is super important. And the question, the way to do this is to evaluate the intra-cluster distance. And so what I'm doing here is like I'm computing K-means for a series of Ks, right? Like maybe start at 2 and end at some reasonably large number that you suspect is kind of like an upper limit on the clusters, possibly in this data set, and then calculate, because it's a super fast algorithm, right? You can just run it multiple times. And then you measure the total intra-cluster distance. So you kind of like The intercluster distance is exactly like that, what you use like in the middle, the distance from the centroids to all of its points summed up, right? And if you do that, if you sum up the intercluster distance for every single cluster, you get some number out of it. And if you plot that over the k's, you will get a graph something like this, right? So for one, this is for this example here with these 5 clusters. For one, I have like an intercluster distance of 30,000. So basically, like, and for 2, I have an intercluster distance of 12,000, right? And so what we see here is very quickly has my intercluster distance dropped. So the solution is clearly not 1 cluster, right? So 2 is much, much better. Then I keep going. I'm going to the 3rd cluster and to the 4th cluster, and there's still like a pretty massive drop. And then the 5th cluster, and it's still a drop. But then if I go to the 6th cluster, it levels off, right? And exactly where you have this knee in your graph is where your k should be, right? Where you have this like where the steepness of this curve tapers off suddenly, that's where you should pick your k. So if you have like a high dimensional data set where it's not like visually obvious, like here, where your k would be, you would plot this intercluster distance, and you would kind of like choose your k based on where this really tapers off. So in terms of properties, it is Loy's algorithm, as we saw, doesn't find a global optimum. It finds a local optimum, but it is very fast. And hence, even if you know your k, it's still super common to just run it with different initializations and then pick the one with the lowest intercluster distance, right? So super common, like you have some multiple iterations and you pick one of them with Kmeans. And it also makes some assumptions about the data. You can kind of like modify this by changing your distance measures a little bit. But mostly it assumes, at least if you have Euclidean distance, it assumes these roughly circular clusters of equal size. So elongated clusters like this are not going to work all that well, or even like clusters that are shaped like this are not going to work so well. And anything that is like not this blob-like pattern is not going to work so well. And so you would have to pick other clustering algorithms for that. Here you could probably do a trick by using some polar coordinates, right? If you know that, but that's like a pretty specific situation. And then another property of K-means that is like often a problem is that we might have unequal cluster size. And so here in this example, you have a very dense large cluster. And then I would argue that you have here like a smaller cluster, and here's like a medium sized to small cluster. And K-means tends to end up with a solution like this, splitting up the big cluster, because all of these points get a vote, right? And if you have a very dense cluster in the middle, and they all vote for the center to come closer, then that's problematic, right? And so you could conceivably come up with some kind of function that helps with that you penalize longer distances or something like that. But like nothing super generic here would work super well. DBScan is another clustering algorithm. That is, the DBScan stands for density-based spatial clustering of applications with noise. I think this is like a super smart idea. Clusters are treated here as dense groups. And the rule is basically if a point belongs to a cluster, it should be near to lots of other points in the cluster. And that's also how we as humans think about clusters, right? It's super intuitive. And so DBScan can actually pick up clusters like this, right? Because it has these continuously close points around this ring and around these kind of like like these concave structures here. And you have 2 parameters to pick in DBScan. One is an epsilon. This is kind of like the threshold of what you consider close. And the second parameter is like a min points. So what is the smallest cluster? DBScan considers outliers. So instead of having like a cluster of 2 points out here, it says like if you have a minimum of 3 points, it would just say those 2 points here are outliers. And so how DBScan works is kind of like well explained with this algorithm. So what here my two metrics here are is the point size, and these circles here represent the kind of like the neighborhood that I'm looking for, right? So in this case, like I'm looking for very large neighborhoods. In this case, I'm looking for smaller neighborhoods. And then here I have my number of the minimum points, right? And so if I run this now, you can see I start with some random point, and for this point I draw a circle around it, and all the points that are in that circle are now considered to be in my cluster, right? And if I reach, like you see this point here, that is beyond that threshold. And if I reach, if I have no more points in that cluster left, in the neighborhood left, I randomly pick another one. And so I get to the result here. And now, yeah, we've seen this has two outliers. And now let's look at our pimpled smiley face here. And let's run this. And what you'll see is this will take a bit, but it will find its way around the circle here, right? And so it's kind of like a pretty cool idea. And let's say, yeah, I guess you always have to be careful, of course, with parameters, especially like in this case here, for example, if you pick your parameter too big, you might connect those elements here, or you might connect it around here, right? So you have to be slightly careful. Let's see. I hope any questions while this is working its way through here. Interestingly, in my observation and practice, all the data sets I've tried so far, real data sets where your cluster data structure isn't so evident, DBScan didn't perform much better than Kmeans. And so it's kind of like an intellectual argument, and it's probably true that DBScan performs better for some other for some situations, but Kmeans has been like a good default. And like here, see, we have like this is like clearly not an ideal solution. We should have adjusted this parameter a little bit, right? But it's always hard to tell. Okay, so now let's talk about hierarchical clustering. And so the principle of hierarchical clustering is that instead of coming up with like a discrete number of clusters, I'm creating a tree of similarities between items. And so what you see here on the right is like what's called like this is our heat map, and then on the left of it is a dendrogram, and this dendrogram visualizes how close two elements are and which elements are in one cluster. And this dendrogram, of course, this is sorted so that you see these nice patterns here. And so the dendrogram can be like read also in the here in the x direction, right? And the height difference, or the height here, tells me how different two clusters that are being merged are. So we can see that here, this part here represents this red cluster, and this tree here represents this whole overall green cluster, right? And so they are the most dissimilar pieces of this data set. And so that's why we have this very high bar here on the side. And so I'm gonna try to draw out this on an iPad. Let me see if I get it done quickly. I'll do it on an iPad so that people on the video can see it. If it takes too long, I will fall back to the Blackboard. Okay. Great. So let's suppose I have these points here. Okay. Let's suppose I have these points here, and I want to do like hierarchical clustering based on them, right? And so what I can do, there's different linkage algorithms. There's the minimum linkage algorithm, or there's like a linkage with centroids. And let's start with minimum linkage. It's kind of like initially they're the same, right? So what I would do is, like, I have two things here. I have the clusters into these, or the points into the space over here, in this area here, and then I have the clusters in this area here, and then I have kind of like a record of my elements down here where I'll be drawing my dendrogram, right? And so we'll be looking at first, like, what is the smallest distance between any points here? And what we'll find is that these 2 points here are the closest, right? And so what we'll do is we'll link them. And so now these 2 points here on the right are considered to be one cluster. And the way that minimum linkage works, that it just looks for which is the closest points to all of the other clusters. And so now we're looking at what's the distance from here to here, and what's the distance from here to here, but we're also comparing it between all of these other possible different distances, right? And so here it looks like that this here is the smallest distance. So this here is the next kind of edge that we were drawing. And so one thing I forgot earlier, E to F is, I would draw my dendrogram like this, right? These are very related. And then A to B here, they are like not quite as related. So I would probably draw my dendrogram like this, right? And so I have now 2 clusters, 1 and 2. And now I keep searching. And then I might kind of like look around and compare what are those distances. And I'm looking here now, because of minimum linkage, I'm looking at C to A and C to B separately. And I would just choose the shorter distance between them. And similarly, D to E and D to F. And so it seems to be that here the distance from D to E is kind of like the next closest one. So I would just draw a connection here. And then this is probably like a little bit more than A to B. And so I would draw like my dendrogram like this, right? And then I could keep going. I would probably determine that this distance here is the minimum. So I would draw this line, and then I would draw the C to D. Okay, I guess it still works. Then I have our C to D like this. And then I will finally draw C to B like this. So then I have my dendrogram. And now I could nicely cut my dendrogram here, for example. And then I would say I have now discrete clusters that are A and B, and then C is its own cluster, and then D, E, and F are in its own cluster, right? And I can cut this dendrogram dynamically. So for example, I can take it down, or I can take it up, right, a level. And so if I were to draw this now here, I would have A and B, and then everything else would be in one cluster, right? And I don't need to compute anything here. This is like basically free, so I can dynamically refine these clusters. And then the other option here would be linkage with centroids, and that's kind of like the same principle, but the only thing that's different here is that how I pick my distances, how I calculate my distances between the clusters is different. So this would still be the closest here, of course. So I have my E to F connection here, but now instead of like looking for what is the closest between any of the points, I introduce like a new centroid, and that is in the middle of these 2 points here, right? Instead of E and F, I'm now only comparing the distances to the centroid. And I would probably still say A and B here is the closest. And then I would maybe say that this cluster to D here. So I guess the end result, in this case, here we have our X here, our X here. And now we don't know, it's hard to say visually, but maybe this here is now the closest relationship. Now this would be like roughly somewhere here would be our closest, our centroid now. And then I would connect this here, right? So I have the C1 being connected to this cluster, and this one like this, right? So basically just a different way of connecting the distances. Any questions about this? Okay. Great. And so there's others. Like I demonstrated the centroid distance and the minimum linkage distance, minimum linkage distance, but you can also have a maximum linkage distance or an average linkage distance, right? So in all of these algorithms, it's just a choice of a parameter, and of course you'll get slightly different results depending on what you choose. And for visualization, as I mentioned, these dendrograms are great because you can dynamically cut them, right? And so here's like a visualization technique where you can like draw this cut dynamically, and you would get these discrete clusters shown here depending on where you cut them, right? And so that can be something super powerful for, especially for data visualization. This is exactly what this hierarchical parallel coordinates algorithm uses. This was the example that we talked about when we talked about tabular data, right? Okay, so next I want to do a design critique. I want to use a design critique that uses projection because this is going to be our next topic. This is a paper actually by Marianne Dirk and Sheila Carpendale. And you get a few different data sets here to play with. You can go to this mariannedirk.de edge maps demo, or you can go to this Google thing, but I also have a handout for you that I'll hand out in a second, and play with it. And these are kind of like different artists. What I'm showing here are musicians, but there's also poets and philosophers in this example. And so let me just hand out these sheets. Yep. Yeah. So if you brought a computer, definitely go to the tool because it has some inductivity. It makes it a bit more interesting. Sorry. Mm-hmm. Mm-hmm. Okay, so let's talk about this. The first question is, what is the data that is being shown here? People or bands. And I'm using the musicians here as an example, because that's the data set I'm most familiar with. Okay, people, and you know, what else? Like the people are the items, right? But what's the data? Significant influence of certain groups to each other. So yes. And what would be the data type? Yeah, network. And more precise. Table. So if whenever you answer network and table, it's hybrid, right? It's like a multivariate network. So it's kind of like along the lines of the lecture last time. What we're seeing here first in this view is probably just the tabular data, really. And the networks really come in only, like the network aspect really only reveals itself on interaction, right? But it is actually both. It is both tabular and network data. Okay, so how is the data types, like how is this visually encoded? Yes, the radius of the circle is the influence. Okay. Yeah. Yes, on the timeline, this is this one here. We have like a 1D positioning, which is time. Notice though that it is not linear time. You know, here we have philosophers, and we can see that there's like, you know, everything from here is 1700s onwards. And then in the 1900s, we had like between 1900 and 1910, philosophy must have been like a very profitable business. There's lots of philosophers and like more notable philosophers in that time span than, for example, since between 1940 and 1950 or anywhere in the 1800s, right? So yes, and then what else? What else is like? How is the data encoded here? Color, yes. So we have color, and what does the color mean? Yeah, I wouldn't call it genre, but of the artist or person. But yes, so color is kind of, and that's the important piece here is similarity, right? Like what's the X and the Y position? Well, I would say it's a redundant encoding. The color and position encode the same thing, right? And both encode some kind of similarity, and both of them essentially do what is aggregation, right? It basically uses an algorithm to project a very complicated set of data vectors down to 2D and places them in these 2D maps then, so that we have these kind of like, you know, what this here means is that if two items here are close to each other, the algorithm considers them to be similar, right? And so have you played around with this? Does this make sense? Like, would you, for example, say the Rolling Stones and the Beatles here are more similar to each other than they are to Kraftwerk? Yeah. Yeah, that's a good question. Well, so one thing that we can learn here is David Bowie is in his class of his own, right? But it is, you know, what's probably happening here is that you run out of, like, you know, the variation on the color scale is probably not completely nicely linear, so that you have some kind of like, you know, this should be more different. I agree, given the positioning, but it's probably a weakness of the color map. Okay, and so what happens then if I so basically the next question we had is the data plotted directly or is it abstracted? I guess we've already answered that, right? It's really like we don't plot something here on an X and a Y variable, at least in this plot, but we rather plot like a pretty complicated aggregate measure for each of these people. And so we kind of like make a data set that is very complicated, accessible in a sense. And then how is interaction used and why is interaction used? Exactly. So interaction really here is used as a way to filter out clutter, right? So in that sense, it also fits nice in the lecture today because it wouldn't, like, if we showed all of these edges that exist here, like music and philosophy and also all sciences and so on, they are super cross-referential, right? People are influencing each other. And if this was a very dense network, and if we showed all of these edges all the time, it would just be a mess. But instead, if we have like interaction, we can kind of like clearly reveal these relationships, and we can also show those labels. So, and the timeline and the similarity views, like what are the two different tasks between that these each support? Yeah. Yeah. So we have relationships, and like what I find the most intriguing about this plot is like the temporal influences. We can see them nicely, right? And we have people like David Bowie, who he was of course influenced by Chuck Berry and the Beatles and Rolling Stones and so on, but he also influenced people that started their career before him, and he was influenced by people started their career after him, right? That's something that we see here. So we have these different types of edges. And I already talked about the nonlinear scales, which is more evident in the philosophers. And so how do you think, like if I gave you a homework that all it said is implement this, where would you get the data? Wikipedia, and how would you approach that?
Search each, like look up all the musicians, and then they usually have like a background tab, so to see every other artist.
Exactly. So that's exactly the approach that they probably took here. So you can look at the links from that article, right? And if they're linked from that article about that artist, they are probably influenced by. You could also do something more smart about it, right? You could try to understand the language in the article with NLP to see, did they collaborate or were they influenced by or whatever, but there's many different ways. I think this data set is actually from Freebase, which used to be like a knowledge database that used Wikipedia to capture these kinds of relationships, but also did some curation on top of it. But Freebase now I think is dead. There is something like this from Google, but I'm not completely sure about its status, whether it's publicly accessible. Okay, overall, yeah. Yes. So we can look at an example, right? We can look at the Beatles here. We know the Beatles started a career in 1954, which is like where they are placed. So that's probably their first album. And they kept going until like mid 60s, right? So they would fall somewhere here. But that's a choice that they made because I'm assuming, if you wanted to visualize career length, then you would have to abandon this circular thing, right? Then you would have to do something with like, remember when we looked at the connected China visualization where we had these stages, how people progress through the career path. So you could do something like this, right? You could have like a matrix on how were people active, and you would also have complicated things, right? Like bands, especially, they start, they break up, they get together again, they change members, right? And like there's lots of complexity and nuance in that. That is really hard, and so that's I think why they made the simplifying assumption here. Like first album, first time you made it on the scene, basically. This is the point that you're shown. Oh yeah. Okay. Yeah, so it might. Yeah, you're right. He was born in 1940. So I guess they that is actually like pretty bad, right? They seem to have, for artists, they have, for individual artists, they have birth year, versus for bands they have the founding year, right? So they should really use the year of the first album instead. Okay. Any thoughts? Do you like this or dislike this? Like in terms of visualization? Like it. This is not a newspaper piece, and I just like, this data is interesting. I think it kind of like has interesting affordances. It's well done. It lets you engage. It's a mix between like an informative visualization and an art project, right? And so that sense, I think, and it does pretty well. And any other comments? So next time, what we'll do is we'll look at the algorithms behind this a little bit, and what are the problems with these kinds of algorithms. Like, these algorithms tend to be extremely complicated, especially the modern ones, T-SNE and so on. And so we'll just be trying to build some intuition and not get into the math. But it's still important to understand how they work and what you can expect from them and what not. And so we'll do that. And then we'll be talking about design methods and evaluation methods. Next week is going to be a last week of like me lecturing, and then after that we'll have project presentations that are just the videos being played, so you don't have to prepare for that. And then on Thursday we'll have the final exam after that. So in the meantime, happy Thanksgiving, everybody, and see you all on Tuesday next week. I would think it's correct, but I like, what is it weird or? Oh, for the last one. So, okay, you want to come down? I can talk to you about this.